Great. Good morning, everyone. Thank you so much for coming to my talk. Um, my name is Zubin Jacob. I'm from Purdue University. Before I start, I want to thank the organizers for inviting me. It was a bit of a long journey getting here, but I'm really, really happy that I'm here. I had also visited ICTS many years back when they actually did share a campus with IISER many years back. So it's really nice to see the growth, and also nice to see a lot of members, not just from India, but from around the world, working in the broad area of spin, orbital angular momentum, spin-orbit coupling, and these areas that we have common interests about. So I'm going to talk about the work done in my research group, and I'll focus a little bit on the theory and the experiment, and I hope to kind of tell you about some experiments. The previous speaker did a great job of really putting a lot of the ideas of orbital angular momentum to the broad audience. I'm going to talk more about the spin aspects. So what I did do before I came is I knew that this is not just a standard conference, but it also has kind of a tutorial style feel to it. So I printed out just a summary of my talk, and I've asked the team members to kind of distribute it. So thank you so much for doing that. This is something just of a way for you to keep a record of what you're hearing, and maybe there are some things in there that while I'm speaking, if you want some more details, you could just go to the link by scanning the QR code on the piece of paper, and you'll probably get a lot more details if there are some things in here that are unclear, or maybe you want to go and look at it in more detail. I also have some long derivations in there, so for some of the theorists in the audience, in case the theory is of interest, you may scan and the QR code on the theory aspects, and you'll see a lot lengthier derivation than, say, in the papers. And this may be very helpful for your PhD. I figured that this may be helpful. Before I start, I want to actually acknowledge my research team. We are 80% experimentalists, and we continue to do theory because I have a theory background. So there's a 20% of the group is theorists, and most of the stuff we do has some theory as well as some experimental flavor. And broadly speaking, today you'll see some aspects of materials physics and also quantum optics put together. So once again, everything that I'm presenting today, all the credit goes to my team, both on the theory and experimental side. So the outline is as follows. I want to start by talking about theory. I'll talk about quantum fields in the start. So that's the first two topics of my talk, and the final three topics, these are experiments. And the key difference over here is that I will be talking about quantum fields in my theoretical section, but the experiments that we are talking about, you should think of them in terms of classical fields. Say classical fields with large photon number, light coming from a laser, for example. That's the experiments that we have been looking at. But the theory itself applies both to the classical limit as well as the quantum limit. So that's kind of one key distinction. And I'll start by talking about focusing on the spin orbital angular momentum, specifically that of light. And for the experiments, I'll talk about a few different systems. One of the first systems is trying to understand this spin angular momentum of light by using NV centers, nitrogen vacancy centers in diamond. This is, think of it as a canonical two-level system, as a kind of spin qubit system. So that's the first experimental aspect. The other is more from a practical point of view. I'll talk about spin in surface acoustic waves on lithium niobate. And then finally, I also want to talk about completely incoherent fields, such as, say, the field generated by heating an object, so just thermal radiation and incoherent fields. How do we measure and identify the spin angular momentum of light in this completely incoherent fields? So that's the outline of the talk. And feel free to stop me during my talk if there are things which are unclear. I'll try my best to explain them. So let's start by looking at the theory part. Now I want to talk about the angular momentum of light, but I want to talk about the quantum aspects of the angular momentum. Now, to actually answer this question, we have to resort to quantum field theory. So what I mean by that is, if you start asking the question about what is the angular momentum operators for, let's say, a single photon, and or try to ask the question, what happens to the noise in the angular momentum, you have to try to understand what is light. So in that case, light is actually the excitation of the gauge field. So the photon is a gauge boson, and it's an excitation of the U1 gauge field that couples to a Dirac particle. So that's kind of what I've pointed out here, that to identify angular momentum operators, you should really be looking at the gauge field in a lot more detail. When we try to think about the electromagnetic field, we are really thinking about the electric and magnetic fields. And that's what is conventionally measured. But in the QED theory, what is actually more fundamental than the electric and magnetic fields is actually the underlying 4 vector of the gauge. And that 4 vector of the gauge is what couples to the Dirac particle, right? So now you can also ask a question, I mean, why should we be studying at this spin angular momentum in more detail? That's a very clear question about what is the motivation to study this, and you kind of realize that an important fact that in 3+1 dimensions, if you look at any particle, the particles can all be divided into 2, either fermions or bosons, and the key property that distinguishes them is actually the spin angular momentum. So fermions have half integer spin and bosons have integer spin. So looking at the spin angular momentum in more detail is actually a very fundamental question. Other than, of course, our applied interest, it's also very important from a fundamental point of view. So there's an interesting result we stumbled on, so I'm just going to go into the details because I know over the last few days you have a very good overview about the field in general. So I'll go directly into the details of kind of what is this result, is that if you actually start looking at this gauge field in more detail, you can identify some very interesting operators for the spin and orbital angular momentum of the gauge field. And that gauge field, I mean, we've just tried to show this as a Maxwell field. Maybe you have some circularly polarized light, there's going to be some underlying gauge field, and that's what couples to the Dirac particle. Now, to be able to get the spin and orbital angular momentum operators of the gauge field, you can just use the fact that we know the angular momentum operators for the Dirac particle, and this has been tested to a very large extent. So when you actually just go through this, I'll put the result in here. The interesting result that you get is that when we study the Stern-Gerlach experiment and we study spin angular momentum of electrons, we see the angular momentum commutation relationships right here. So D subscript just means Dirac, and this is SDI, SDJ. These are the different components of the spin angular momentum, and they don't commute. And you have this IH bar, epsilon IJK, SDK. So, and then you also see that the orbital angular momentum has the exact same type of commutation relationships, and the spin and orbital angular momentum, they commute. Right? This is for the electron, and this is known from Dirac fields, and we also studied this in kind of textbook quantum mechanics. Now, what is very interesting is that if you actually ask the question about the spin and orbital angular momentum of the gauge field and try to really get answers through the QED theory, what we noticed is that you actually get interesting expressions for the spin and orbital angular momentum. I have printed it out and I'll go show it to you on the next slide. But what I want to emphasize even before I look at the answer is that if you look at these proposed gauge field angular momentum operators, they obey the exact same, there's an exact symmetry between the commutation relationships for this as well as the Dirac particle. So in some sense, the gauge boson as well as the fermion in QED, they are going to have the exact same commutation relationships, and this was actually not known. It's very surprising that this was not known to the community even today. So I mean, till our paper kind of put this forward. And there's a lot of interesting work. I will not go through kind of the previous work because the tutorials have probably covered a lot of details about that. I want to go through what are some of the key steps to actually getting this result. So the key part is to be looking at not just the global angular momentum of the field. You have to look at the density, which is the spatial distribution of spin and orbital angular momentum. How is it distributed in space? And that quantity is what actually, if there's an electron, the wave function of the electron couples to the local kind of gauge field, and you essentially have this density that comes out of there. So what you start with is just for the Maxwell field, you write down the Lagrangian density, and this is actually a very specific form known as the Fermi Lagrangian. It's a gauge fixed Fermi Lagrangian. And then what you do is that you impose on this Lagrangian the condition that there should be some invariance under translation and some invariance under rotation, and from there you can derive the conserved quantities of this gauge field. And that's basically what comes through Noether's theorem. And when you apply that, you actually see an interesting result that from this, just this invariance to translation and rotation, you see an interesting result that you get two operators which has the concept of the density. This integrand here is a density, it's a spatial distribution, and this is the total spin angular momentum for the Maxwell field, and this is the total spin angular momentum for the orbital angular momentum for the Maxwell field. And what really is important, and I'll focus on the spin part for my entire talk, is that you see an interesting expressions right here. There's the vector potential A, and there's a cross product with the canonically conjugate momentum to the vector potential. So you think of it this, in some sense, this is like an x and p for the gauge field. I mean, x is sort of a position variable and p is sort of a momentum variable. So that's one way to think about it, but as you know, I mean, these are not, the gauge fields have to be handled with care. Yes?
All these A's and all these quantities, they're usual Lorentz-Ford vectors.
Yes. Yeah. Okay, so let me try to explain this. In this case, since we are looking actually just at the spatial part, this is a 3 vector. Yeah, this is actually, and so that's a great question. This is A is a 3 vector.
4 vectors, that's the reason I'm asking.
Yeah, we have to.
Or you just take the spatial part.
You just take the spatial part, right. And then you take the cross product, and this is actually a vector. So the spin and orbital angular momentum, as you would expect from intuition, are vectors. So, and so now, once you get this, we impose the equal time commutation relationship on the vector potential and the canonically conjugate momentum. So if you impose this equal time commutation relationship, you actually end up getting the 3D canonical kind of angular momentum commutation that we do expect to see from, say, Dirac particles. So Dirac particles have the same thing. Have the exact same relationship. And what is kind of interesting in here is that if you actually go through this prescription carefully, you can show that the Dirac particles will obey this and the kind of gauge bosons will obey the exact same commutation relationship. So on the same footing, you can actually look at both of them. So that's what we call kind of the QED gauge field and the spin density. So in case you are interested, the theory students may be interested in a more detailed derivation, if you can scan the QR code either right now or it should be there on the printout, you'll be able to see all the steps needed to actually get this result. Now coming to what is experimentally observable, we have to be a little more careful. What you need to now go and look at is that in free space, you have only these 2 transverse degrees of freedom for light. And so you need to also be very careful that the observables that you think about are gauge invariant. So once you perform that gauge invariant and you do it both for the Dirac sector and the Maxwell sector, you actually do get the commutation, the expressions that you do know from, say, Cohen-Tanuji's textbook and others. That happens after you do the gauge invariant decomposition. So this is the spin angular momentum density. This is the kind of electric field transverse part. This is the vector potential transverse part. This is an observable quantity. This is an observable quantity, and the spin angular momentum is an observable quantity. The other important thing is you can show for these expressions, if you actually just go through the integrals, that they commute. So in principle, for a single particle, we can construct the operators such that these two operators commute, and then you should be able to independently observe them, and they're also gauge invariant. So this is actually an important kind of step for us to now go and look at, okay, what are the type of observables that we are interested in, and can we start observing them separately? So we did a theory paper where we looked at the quantum limit of the very well studied and well understood classical limit of say classical beams carrying OAM. So this is the classical limit. Now let's do one thing. Let's actually look at the same type of OAM beam, but let's say that there's only a few photons in that pulse. Let's also make it into a pulse. And this is what we're trying to depict here. There's some OAM and in this beam, but now let's say you just switch it on and off, and you also actually have only a few photons, and it may also be one photon or a few photons in this quantum limit. Now, for this twisted single photon wave packets, we can start looking at the spin and orbital angular momentum in more rigorous detail, because now we really know which are the operators that commute and so forth. So I'll give you the answer in the start, and then we'll go through the details. The answer is as following. You get all the many classical results that we know and understand really well. I mean, all of those things are retrieved, but you also get some extra things, which is the fact that from these commutation relationships, you can show that there's going to be some unique fluctuations in the orbital angular momentum, and these come from the commutation relationship. So just going back to the previous talk, there was some very interesting discussions about the ring BEC and very high orbital angular momentum, like the hypersonic and supersonic limits. What we are noticing in our theory is that as you go to these large limits, if you increase the orbital angular momentum in, say, in one direction, along the transverse direction, the fluctuations of our orbital angular momentum will increase. So this result cannot come out of a classical theory, and that does require a quantum theory to look at. And those are the type of observables which would be interesting to look at. So the noise in the spin property as well as the OAM property. And there are some other properties as well which are non-local spin noise. So looking at the properties, not just at one point or measuring properties at one point, but looking at correlation functions of spin-spin correlation functions for the light field. So these are some interesting things that can come out.
How are you distinguishing between classical and quantum limit? Because what is the difference in terms of commutation itself? Or are you saying commutations which you were showing in the previous slide, they are same in both of them, or what is it?
Yeah, so let me clarify. The commutation relationships definitely are the same, right? Absolutely. What we are really saying is that the quantum limit just means that there are few photons in the pulse. Here there are, say, millions.
No, but I'm asking, what is difference? You are talking quantum versus classical. Number fluctuation in the photon is that?
So you can think of it as number fluctuations in the photon is definitely one. But more easier way to define it would be to just say that this has a very large number of photons and this has a smaller number of photons. So the photon fluctuations are way more pronounced in the quantum limit than in the classical limit. The number fluctuations of the photons are more pronounced because it goes as 1 over square root of n.
No, like
right.
Just for the massive particle, when you spin,
right.
Like angular momentum. So quantum versus classical, the commutation relation which we draw, right?
The commutation relationship is the same, right? Because you have to apply it at the single particle level, right? So the commutation relationships are the same. What I'm really talking about is the kind of experimentally measurable consequences of the commutation relationship. That is very tricky. The experimentally measurable consequences are tricky to isolate. That's what I'm trying to say. Yeah. If you only look at the classical limit, yes.
I have a question related to non-local spin noise.
Okay.
So do you mean that the spin fluctuations are correlated fluctuations?
Yes. That's exactly, yeah. And to understand those things as well, you need a quantum theory, right? So I'm trying to kind of identify the aspects where the quantum theory is useful. Yeah.
So coming back to this, so you mean these correlations are quantum mechanical in nature?
Yes.
Not
yes.
Classical correlations.
Not classical correlations. Yeah. Yeah. Now, Now I should kind of also specify that we have not studied, let's say, spin-spin entanglement in the field and so forth, but those are things on the cards. So we'll have to do it more carefully. Yeah.
One more question. So, in the non-paraxial regime, beyond paraxial approximation, there is a spin-orbit interaction. In
Yeah.
that case, does commutation relations hold?
Oh.
That are non-zero.
Okay, so the commutation relationships hold, and they hold for these quantities. Now, the commutation relationships are indeed modified based on these vectors right here. So the one I showed you before, let's look at this one, right? This is actually for the gauge field themselves.
So for example, this one, all these things,
Yes.
these are only quantum mechanical, right?
Yes, exactly,
There
yeah.
is nothing like classical analog of
I agree with you on that, yes.
But then the other side you are saying they are same.
No, what I'm trying to say is that, no, that's not what I'm saying. I'm saying that trying to identify the experimental consequences of this cannot be done classically alone.
No, I'm not
Yeah.
saying about your aim all this. I'm
Right,
saying
okay.
For massive like spin fermions. you are saying.
Yes, yes.
So for fermionic like electron spin,
Uh-huh.
you don't have classical analog like that. But will you call there is also classical?
And I agree.
Commutation, I'm saying about the commutation.
Yeah, so here is the thing. The light field, the gauge field case is a bit more tricky because
So then what is classical quantum? I'm not able to really appreciate that.
okay, so let me put it this way: for the commutation relationships,
I have a suggestion.
yeah,
It's
we can talk over coffee.
of course, it's a discussion meeting. There is a definite point in having discussion. But try to have quicker discussions in between the lectures. Okay, after the lecture, you can ask.
We will talk over coffee, right? So that I can get through all the experimental part as well. But I appreciate your question, definitely, right? And I'll come to kind of the question about the angular momentum as well. There's some details over there that we can discuss over coffee. Yeah. So I'll move ahead to kind of just discuss the results quickly. So let's now apply this kind of angular momentum commutation relationships and other things. Let's apply it to a pulse that we have definitely studied before. This is just an example. You can apply it to any different beams that we have studied in free space. Right? So this is a Bessel pulse, so you can look at sort of the energy density, the Bessel beam profile. These are very well understood classically. And now what you do is you define your operators carefully for the creation and annihilation and make sure they are consistent with the previous densities, because every point in this beam is going to have some local spin angular momentum. So that's very important to remember that the beam has a spatial profile, and we are talking about the density of the spin angular momentum, the spatial distribution, and looking at it. So the mean value is kind of well understood, and I think this should be able to, with the mean value itself, you can probably get it classically as well. And this is the vectors at a certain position, and they have some interesting texture in them. The reason we call this as spin texture is the word is really kind of borrowed from condensed matter physics, where in certain types of magnets, instead of spins all pointing together or pointing, say, in an antiferromagnet, there are kind of opposing spins. Spin texture really stands for the word that in some magnets you can have spins which have some winding number, or the spins have some special direction to them. And we are actually seeing the exact same thing for light, and this is the mean value, as I pointed out here. And this probably could be analyzed classically as well. Now, what is important is that there are quantities such as the fluctuations of these spin and orbital angular momentum density. So that's the variances, not the mean field. And those variances will be very different if you create a Fock state twisted light pulse or a coherent state twisted light pulse. So a Fock state is a deterministic photon number state, and a coherent state is like a very similar to, say, the light coming from a laser. It's essentially the light coming from the laser, and these are photon number fluctuations. It's not a deterministic photon number state. So the orbital angular momentum and spin angular momentum noise fluctuations are going to be very different in these two cases. So that's what kind of the theory predicts. And so these are kind of the things that we can measure in principle. So this is the photon number on the x-axis. This is the variance of the orbital angular momentum in the transverse plane. So that's really important because we are creating a angular momentum state along the z direction, but the measurement is in the direction perpendicular to the direction of propagation, and these scaling laws are something that we can analyze and understand in more detail. And another important thing is that as you create large orbital angular momentum states, these fluctuations go up. So there is a motivation to create large angular momentum states because experimentally it will be more easier to measure these fluctuations. And another thing is that, so this is work under progress, is again we are trying to look at the 2-point correlations of the angular momentum in a light field. So these are spin-spin correlations, and I think in the few photon number limit, there are some interesting things which are different, even though you are looking at, say, n equal to 1 state, an average photon number of 1, either it's a Fock state or a coherent state, there's actually difference in this spin-spin correlation. So this is another interesting thing that comes out of the quantum theory, that in the classical theory you will actually get the same result. So these are the quantum fields aspects that I wanted to mention, and now I'm going to change gears to talk about experiments. And for the experiments, I'll repeat this, that we are really looking at the large photon number limit, we are looking at the classical fields. And I'll try to just go through these 3 experiments. Let me try to understand how much time I have so I can pace myself. 15 minutes, right? Okay, that's pretty good time. I'll just maybe spend few minutes on each of these experiments. So the first experiment, it was actually trying to look at this local quantity. Now, if you give a complicated orbital angular momentum beam and you try to study it, most of the techniques to study it really try to understand the global properties of the field. We are very interested in the local properties, so we were thinking what are the ways that we can actually start probing it with a very high level of sensitivity. So that's where this idea came from, is that let's start at the very, very basics and let's start with the simplest experiment that we can do. So what we did was we took a Gaussian beam, this is just light from a laser beam, and then you just construct it into a circularly polarized light beam. Now what you do is you focus this light beam, this is just from a diode laser, and you focus this onto an AFM tip. Now, what is special about this AFM tip is that the end of the AFM tip is a single nitrogen vacancy center. What you can think of this as a single 2-level atom, and what makes it interesting is that it does have this 2-level atom properties even at room temperature. So that makes kind of dealing with experiments much more easier than having to really go at low temperature. That was our motivation to do this. And this also, another very important thing about the NV center is that you can initialize this nitrogen vacancy center optically, and you can control it with microwave fields. So you can perform some Bloch sphere rotations, and it's really like a qubit system. So when this light field is incident on here, what happens is the phase of the qubit changes, and that phase of the qubit changes according to the local spin density of light. So I will show that theory result. This is just helping you get a mental picture, and you can then probe at the location of this tip, you can probe what was the spin density. And with some effort, you can even get the direction of the spin vector field. We also repeated this experiment trying to really understand it. We've also recently done it at low temperatures, but this was another experiment we did. We went away from the single emitter limit. We looked at a bulk NV center, and we tried to really figure out what happens when you have this light interacting with the NV center. There's an induced effective static magnetic field. Think of it as the spin density of light creates an effective static magnetic field at the location of this NV centers. So let's try to understand this interaction in more detail, and then I can talk about the experimental results. So for those of you who are interested, there are many review articles on this. There's an entire field of research that deals with trying to look at these defect centers in diamond. So think of this as the kind of lattice of carbon atoms, and then you have this vacancy, so one carbon atom is missing, and the other carbon atom is replaced by this nitrogen. So this system forms a very pristine system on which you can do 2 levels. Yeah. In this previous slide, we are not scanning right now. The goal is to actually scan, but right now the AFM tip is only because you can isolate that one NV center very easily. That is the reason. Yeah, think of it that for this case of this experiment, that's all it is. Yeah. Thank you. So I think it's very nice to go through these reviews in detail. From a broad perspective, just try to think of it as a two-level atom and it's a spin qubit, right? So there are ways to characterize this, which is now standard in the field. You can actually look and isolate single NV centers. What you're seeing is actually a confocal image. This is the x-axis, this is the y-axis, this is a diffraction limited image. And this is the spot size, and you can actually see, if you look at this kind of color bar, that there's not a lot of photons coming out from every NV center. So these measurements are a bit time consuming in terms of generating the photon statistics, but this is low photon level imaging to just isolate the NV centers. You can really prove that there's only a single NV center in each of them. And then finally, by applying microwave fields which are resonant with this two-level atom, you can scan the microwave fields and try to study this contrast, and you'll see that this contrast goes up and down depending on the frequency, and that helps you isolate the resonances and get a good understanding of the level diagram. The other thing is that even at room temperature, you can actually easily get Rabi oscillations between the two-level atom, and that is also manifested in the contrast of the light field, and this is the RF pulse length used for kind of creating specific states. So once you know these the exact Rabi oscillation frequencies and you know these oscillations, you can actually create the state, a superposition state between the ground state and excited state as required. So what we did was, for the NV center, when you have the circularly polarized light, if you consider the level diagrams very carefully, you can show that for that spin qubit interacting with the spin density, the phase of the qubit will be perturbed. And you can think of this as a spin optical Stark shift. And we have a detuned laser beam, so the absorption is very low. So this, the phase of the spin qubit is perturbed, and that phase perturbation, you can think of it as an effective static magnetic field that is coming from your applied light field. But when you go through this entire calculation, an interesting thing comes about. This static effective magnetic field only depends on two things. It depends on, of course, your frequency of the laser, and this has to be detuned. But other than that, it depends on the direction of the NV axis. What is the magnetic dipole moment axis of the NV? And a dot product with the spin density of light at the location of the NV. That is what I mean by this S vector observable. You can relate this to the E perpendicular cross A perpendicular vector quantity that I had showed in the previous theory slides. And if you go to the monochromatic limit, you will get the kind of popular expression, which is E star cross E. So because of this, and then we did some of the theory, and we realized that there are some kilohertz level splitting that we can read out even at room temperature. So we went ahead with the experiment, and when you try to read this out, one has to be a bit careful, just because we are reading out phases, and I hope this movie plays. I'm just trying to show here. So I think I'll escape and then play the movie. This one should play. I hope. Oh, it says cannot play media. Sorry about that, but let's go back. So what you would, if the movie did play, what you would see was just, you have to perform a few block sphere operations to be able to read out the phase of the qubit. And this is known as an XY8 protocol and the Hahn echo sequence in literature. So I'll let you go through the paper to kind of see the details of how we read out this phase of the qubit. And the phase is represented in units of nanotesla because it's an effective static magnetic field. This is a room temperature result. Now, as you simply change the ellipticity of the light beam using a standard quarter wave plate. So nothing interesting on the x-axis over here. What is interesting is really the nanotesla static magnetic field, which is coming from the phase of the qubit. That does follow the theory extremely well. So that gives us confidence that we can now start looking at much more interesting experiments with this system. So think of this as kind of a benchmarking that indeed the monochromatic limit of the spin density of light can be imprinted on the phase of the qubit. And the other important thing is the kind of target beam power. As you increase the theory also gives a linear dependence, which does match the experiment without any fit parameters. So with that, I'm just going to use a little bit of time to talk about these two other experiments, which is slightly more on the engineering side of things. We are really trying to see, now that we understand spin very well, and of course the community does, what are some of the applications that we can think about. So another classical application is that of looking at the acoustic waves on lithium niobate. So lithium niobate is a material that is used widely in industry. Surface acoustic waves themselves did have many industrial applications, but one aspect of a surface acoustic wave, which is the local spin density, was never measured. So think of it this way, this is lithium niobate, this is a substrate, there's vacuum on the other side. The color scheme that you see here, the dark and kind of bright color scheme, this is really the surface acoustic wave as propagating. There are deformations of the lattice. So it's a kind of, think of it as a pressure wave. And that deformation is what is shown here with bright and dark. As this surface acoustic wave propagates, near the surface, the pressure field couples to the electromagnetic field, and the local electric field rotates near the surface. And the rotation direction is locked to this momentum. So you can think of it as a triplet. There's a spin angular momentum direction. That is the local direction of the electric field rotation. There is a momentum, this is the direction of the surface wave, and there is a decay. There's no surface, there's a surface wave, so there's no real amplitudes of electric or magnetic fields away from the surface. So this is once again the displacement profile and the electric field profile that has a local rotation property. In some sense, this is an effect which was actually predicted like a very long time back. Of course, Lord Rayleigh didn't really connect it to spin or spin momentum locking or any other things. He was just talking about the electric field rotation in a surface acoustic wave, but this was never isolated or measured. So along with our experimental collaborator who did a very careful measurement, we were able to isolate this. So this is a movie, I don't know if this is going to play. Let me try this. Yeah, this doesn't play either, but this is part of the paper. You would see these kind of pressure waves as well as this local handedness of the electric field, which is different if a surface acoustic wave propagates in one direction versus the other direction. So the experiment is as follows. What you do is you take a substrate of lithium niobate and you have an RF transducer. So this will be something that actually just literally speaking is kind of hitting the lithium niobate to generate those surface acoustic waves. So the surface acoustic wave goes here. The pressure waves are set up. That's what is shown in this small cartoon schematic here. The electric field starts rotating. And now you want to measure this rotating electric field. So what was the clever kind of innovation from the experimentalists was they constructed a three-dimensional quantum well over here. And you excite the quantum well with a 660 nanometer laser. And then you study the unique photoluminescence spectrum coming from this nanowire quantum well. There's actually two wavelengths that come from this quantum well, and these two wavelengths are modulated as the surface acoustic wave passes through. For details, you can actually look at this paper, and the key experimental result is as follows. It's really in this figure. As your surface acoustic wave goes through, the electric field starts oscillating. As your electric field starts oscillating, the electrons in the quantum well perform a cycloidal motion. So for some time they are in this red region of the quantum well, for some time they are in the blue region of the quantum well, and they keep rotating. And the intensity of the photoluminescence at the two quantum wells are different, and they are kind of completely correlated with the time period of your surface acoustic wave passing through. So we think that for lithium niobate, there could be some interesting applications of surface acoustic waves and the spin properties which have not been explored so far. So finally, I'll just take a few minutes to talk about, again, this theme of spin density, but now we want to generate this using completely incoherent radiation. So think about it as heat radiation. Now, kind of thermal radiation really forms one of the largest sources of information around us. We are really used to the visible spectrum, but the infrared spectrum carries lots of rich information. If you look at this image, this is taken with a thermal camera on the left-hand side. That's the Wabash River near Purdue campus. This is just looking at the intensity of the thermal radiation. And let's say you do this experiment in the night time, so there's no sunlight. So all this thermal radiation is really originating from these bodies close to room temperature. This is the type of image that you see. Now, if you were to actually use a polarizer and look at this image, you will see that the light coming from, or the thermal radiation in the infrared spectrum coming from the water is slightly polarized. This is actually even true from your face. If you were to take a thermal image of your face, just from the contour of your face and how your nose is located, the thermal radiation has some partial polarization of the electric field. But the spin angular momentum is near zero in outdoor environments and natural environments. It's less than kind of 1 part in 10 raised to 5. So that gave us the motivation. Let's start to look at, how do we create the spin angular momentum in thermal radiation? So when we looked at literature, we found that on Earth in general, you don't see this phenomenon. But if you look at just starlight and many astronomical objects, because of the very strong magnetic fields that are created in these cosmic systems, you can actually get thermal radiation which has some circular polarization. But that does require very strong magnetic fields. And there's an interesting paper from 1998 that even says that, if there's some chirality, if there's some handedness of the thermal radiation, it's coming from organic molecules, and that's the place to be looking at signatures of life. So, yes, great. So I'm close to the end now. And so over the years, people have looked at different approaches by applying magnetic field, sometimes using filters, but these are large systems. And we were trying to look at more a metasurface or nanostructured approach to generate thermal radiation. So I won't go into the details, but one way to do it is actually to break both the inversion symmetry and this mirror symmetry in a two-dimensional system. If you can actually break both these symmetries, then you can generate net spin angular momentum even by heating an object. You don't really need a laser or anything else. And the key aspect is you can generate that spin angular momentum in the infrared radiation spectrum. So we did this experiment where what you're seeing on the left-hand side is actually a pretty intuitive design. It's just consists of gold structures which are fabricated on a thin film substrate, and the design of this F structure is just because it breaks all the symmetries. I mean, this is not the only design. You can just think a little bit and come up with many different designs that break the inversion symmetry and the mirror symmetry in this plane. And now if you heat this object, this is the experimental result. My laser pointer is actually, this is out of battery, so this is not working. But if you look at that central figure, that shows the experiment. The x-axis is the infrared spectral region. We are somewhere between the 6.5 and 7.5 micron region. The y-axis is the black body emissivity. So that is the emissivity that lies between 0 and 1. And you can see that for the left circularly polarized thermal radiation, there's a large thermal emissivity, but by heating the object, the right circularly polarized thermal radiation is suppressed. And that's essentially what you see in the black curve. Now, if you define the Stokes parameters exactly the same way as you do it for, say, a laser beam, but now you do the same Stokes parameter analysis for the thermal radiation, you will see that the purity is 60%. And just because of the fact that you've heated an object, but it's emitting more preferentially the one circularly polarized handedness. So this is interesting on multiple fronts because think of this as a partial coherence of the field, but now the partial coherence of the thermal field is really in the spin angular momentum degree of freedom. And this can open up some interesting applications. And we have actually looked at this in more detail by studying the angle resolved and angle resolved emissivity as well as the spin polarized emissivity. There's some interesting dispersionless bands. I won't go into the details. For those of you who are interested, you can actually go through the paper, and there's a really good match between the simulation and experiments to prove that there is net spin angular momentum carried by the thermal light field. And this was not experimentally isolated before. That was one of our motivations to do it in a more conclusive way than what was done before. And you can then consider many different symmetries and analyze what happens to the thermal radiation. So we have some interesting ideas to start looking at topological, say, polarization singularities and others in the thermal radiation field using these metasurfaces in the infrared spectrum, and possibly some kind of practical applications as well. So with that, I want to summarize my talk very quickly. I did start by talking about theory. I felt this would be kind of interesting complement to many of the things that we have discussed at this conference. So I spoke about those commutation relationships and the gauge field angular momentum densities, and also talked about the photon statistics and noise in the angular momentum that does require a quantum theory to understand. Then I switched gears to looking at more classical fields, but a variety of different classical fields, and these were all completely experimental. The one was the spin qubit NV center, where the phase of the spin qubit encodes information about the local spin angular momentum, that is the density of the photon spin angular momentum. And then I spoke about the acoustic wave as well as the incoherent thermal radiation in the infrared spectrum, which in general has no spin coherence at all. But by engineering some symmetries, you can actually build in some spin coherence in that thermal radiation light field. You can go to these websites to get more information. I want to once again thank the organizers for inviting me. This is a great place to be and a very nice opportunity to interact with all of you. I'll be happy to answer questions. Thank you.
Yeah. Thank you, Zubin, for nice talk. We can take 1 and 2 quick questions, and then we can continue during break.
Hi, very interesting talk. So I have a question about this symmetry breaking. So how I understand the detail of the symmetry breaking of the surface should play an important role, right? Means, of course, there may be many shapes which are breaking the symmetry, but how the radiation is coming out, the microscopic aspect of the symmetry breaking, shouldn't it play a role? Because the example what you have shown, so those are macroscopic.
So what I should say is that, the structure sizes themselves is actually smaller than the wavelength of the radiation, right? Okay. So yeah, exactly. Yeah. Right. Sure.
Hi.
Yes.
So again, maybe that classical versus quantum, I was thinking about from your note only.
Okay, yes.
So is it like when I think the classical commutations of those spin of light which you are saying, because you are defining S or the spin itself with vector potential, and so in vector potential itself you have also annihilation creation type operator, right?
Yes.
So do you take those operator as means their commutation is important in quantum case and not important in the classical case?
That is definitely a good way to think about it. So you have these A dagger operators, and you can start saying that in the quantum limit, you have the correct bosonic commutation relationships, and from there you can derive some classical limit where you have a large number of
and
photon numbers. Exactly.
As complex number.
Yeah.
Do you have any experimental results on spin fluctuations?
Actually, none at all. We don't.
Have you ever tried any of that?
I think there is some on the orbital angular momentum fluctuations. I've not gone through this in detail, but definitely not for the spin fluctuations. That we have looked,
So
yeah.
what is the kind of experiment one could go for? What one should measure and how one should measure?
You know, in the start, just starting from the
I want to see the motivation. All these calculations you are doing, you are
Right.
bringing out a lot of interesting aspects. So
Right.
what is the motivation? How one experimentally should approach the problem and measure all those effects?
So the first one to think about would be, you can start with a laser light beam. But generate a very large orbital angular momentum in the z direction. Just an LZ eigenvalue should be a very large eigenvalue, let's say 100 or something. And then one has to think of a way to measure the fluctuations of the orbital angular momentum in the XY plane. And just by looking at how it scales with the LZ quantum number, we can verify the theory, and it'll be in the XY plane. Now, how do you measure the fluctuations? This requires more thinking. Like, I don't have an idea, but I'm sure some clever experimentalist will come up with that idea. The other thing I can quickly say that what we are trying in our group right now is that, so we have a low temperature setup for the NV center. And now we've been able to get the coherence times to be longer. And now we are coming in with an orbital angular momentum light beam. And we are trying to study what happens to the average value of the spin, what happens to the spin fluctuations of the qubit when it is imprinted with a very large orbital angular momentum, quantum number.
Another quick query about your surface acoustic waves. These are standard Rayleigh waves, right?
Yes, they are.
And you excite them with piezo ceramics?
Exactly.
Right.
Yeah, very standard.
Hi.
Yes.
A very nice talk, Zubin. I just have a question from what Professor Dr. Gupta asked. So basically, in terms of the quantization of the spin, the photonic spin that you said, some papers also have read on the quantized Stokes parameters.
Yeah.
So in this context, the quantum noise that we are talking about of the spin, can that be used in the context of some kind of squeezing, like in different degrees of freedom? Like, for example, if you have quantized Stokes parameters S1, S2, S3,
Right.
S3 is the spin,
Right.
but then S3 and S2, so therefore there are like two different quadratures. So can it be used for some squeezing kind of thing?
You know, this is a really good question. I don't have the answer to that, whether we can use it for squeezing. We started looking at that in more detail. Almost always in those cases, sorry, we need some sort of nonlinearities in the system.
Yes.
So then the question becomes, how is this advantageous compared to conventional way of squeezing the light? So I don't have an answer for that, but I definitely feel that there should be something really interesting in this squeezing and spin-spin correlation functions, which has not been done before at all in the context of light, and such as the quantized Stokes parameters. Yeah.
Thank you.
But if you bring in this nonlinearities, your SUN algebra will hold anymore?
Actually, that requires more thought. It's unclear to me.
The whole setup breaks down.
This setup breaks down. Yeah.
Right.
Yeah.
So let's thank Zubin once again.